Assalamualaikum and hi everyone. This is 7.3 part 1. So 7.3 is regarding solubility equilibria. Here are the learning outcomes. At the end of this lesson, students should be able to A. Define solubility, molar solubility, and solubility product, or also known as KSP. So are you ready? Let's go! Solubility and molar solubility. So from the word solubility, what do you think solubility means? Solubility is the maximum amount of solute measured in gram or mole that can be dissolved in a given quantity of solvent to form a saturated solution at a given temperature. For example, in our daily life, we have sugar. Sugar is the solute. In its maximum amount, we mix it with a cup of a bitter tea, and then that bitter tea is the solvent. When we mix up a solute into a solvent, it will form a saturated solution, which is a very sweet tea. Right? So solute mix up with a solvent, forming a saturated solution. Simple. Next. Solubility. Again, solubility, as we know, can be measured in gram per liter or mole per liter. When the solubility is given in gram per liter, how do we define? It is defined as the grams of solute dissolved in 1 liter of a saturated solution. Therefore, the unit is gram per liter. The unit gram representing the solute, meanwhile the liter represents the saturated solution. Apart from that, solubility can also be measured as mole per liter, which is known as molar solubility. The difference is just in the unit of solute. For example, for molar solubility, the solute is calculated in moles. Therefore, it is defined as moles of solute dissolved in 1 liter of a saturated solution. Therefore, there are two units of solubility, which is gram per liter or mole per liter. For example, if the solubility of silver chloride, AgCl, given is 50.0 gram per liter, it indicates that there is 50 gram of solute, which is the argentine chloride, dissolved or present in 1 liter of saturated solution. You know that solubility and molar solubility are interconvertible to each other. But how? Yes, by using the molar mass. So if you would like to convert solubility into molar solubility, you just have to divide by the molar mass. Meanwhile, from molar solubility to solubility, you just have to times by molar mass. Simple. Next, solubility of slightly soluble ionic compound. Assumption, we assume that the small amount of a slightly soluble. What do you mean by the word slightly soluble? That means the ionic compound is not 100% soluble. There must be, at the bottom part, let's say we have a beaker, at the bottom part of the beaker, there must be undissolved solute. Yes, so we assume when we are dealing with the solubility of slightly soluble ionic compound, we assume that the small amount of the slightly soluble ionic compound that dissolves in water dissociates completely into its ion. Right? For example, we have here slightly soluble plumbum chloride. And please pay attention. The state for the slightly soluble ionic compound is denoted as solid. Why? So let's see this picture. Can you see here? Right? In a beaker of a slightly soluble ionic compound, most of the solution is made up of what? Made up of the solute, undissolved solute. This is this part. Meanwhile, on this top part. This is the slightly soluble part, dissolve in water. But this part will dissociate into its ion. Right? So, what PbCl2 is made up of? Cation and anion. So, what are those ions? It is Pb2 plus aqueous and also Cl minus aqueous. Right? So, please make sure when the question give you or state that this is a slightly soluble plumbum chloride. So please make sure you use the solid state, because as we can see, most of the compound is made up of undissolved solute. Meanwhile, there is a small amount of slightly soluble ionic compound here, which dissociate into its ion. Okay, so now the equilibrium exists between that solid solute and its aqueous ions. The solid solute is the one at the bottom part of the beaker. We call undissolved solute. So, how do we write the equilibrium equation? PbCl2, which is the slightly soluble ionic compound, is in equilibrium with its soluble ion. So what are the ions? It is Pb2 plus aqueous plus 2Cl minus aqueous. Right? You have to balance the equation. This is called the equilibrium concentration of a slightly soluble ionic compound. For example, we have argentum sulfide. Argentum sulfide, the chemical formula is Ag2S solid is in equilibrium. So you must use the double-headed arrow with its soluble ion. Ag2S is made up of Ag plus and also S2 minus, and then you have to balance here. Got it? Why? Why you need to learn on how to write the equilibrium equation? Because you will need it later. Right? So when we want to learn about solubility product constant, which is KSP, you must master up on how to write the equilibrium equation first. So what's meant by KSP? KSP is the product of ion concentrations in saturated solution. Product of ion concentration in saturated solution, each raised to the power of its stoichiometry in the equilibrium equation. Yes, this is the equilibrium equation that we learned in the previous slide. For example, you were asked to write the KSP expression for AgCl. So first thing first, before constructing the KSP expression, you must first write the equilibrium equation. So AgCl solid is in equilibrium with its soluble ion, which are Ag plus aqueous and also Cl minus aqueous. Next, it's time for you to write the KSP expression. Based on this definition, can you try how to write the KSP expression? Yes, so KSP equal to the concentration of argentum times concentration of Cl minus ions. Right? Concentration of argentum plus times concentration of Cl minus ions, each raised to its power. Right? Power of its stoichiometry. So this is 1, this is 1. Alright, so we don't have to write that one. So this is the KSP expression for argentum chloride. Clear? Therefore, as I told you earlier, you must write down the equilibrium concentration correctly first, so that you are able to write the correct KSP expression. So KSP, in other way, we said that an equilibrium constant related to the equilibrium between solid salt and its ion in solution, and then it provides a quantitative measure. Yes, you will have to calculate the KSP value during your tutorial session, right? So it provides a quantitative measure of the solubility of a soluble salt. Mind the soluble ionic compounds, which is 100% soluble and dissociate in water, such as NaCl, have no Ksp value. Right? Why? Because there is no equilibrium exists between the solid solute and also the soluble ions. Because when that salt is 100% soluble, that means there are no solid solute in the solution. Right? Therefore, it has no Ksp value. Bear in mind, therefore, Ksp value is only valid for slightly soluble ionic compound. So here is time for some practice. So you need to write down the Ksp expression for each of the following. So there are two steps. First, you must know the chemical formula for each salt, and then you must write down the correct equilibrium equation. Then you can only construct the Ksp expressions. So let's see. How do we do this? So silver carbonate, argentum carbonate, right? The chemical formula is Ag2CO3 solid is in equilibrium with its ion. So its ion are made up of argentum plus and also CO3 2 minus carbonate ion, and then you have to balance, right? 2 here. And then write down the Ksp expression equal to concentration of its ion, each raised to the power of to the stoichiometric power. So we have two types of ion, Ag plus and CO3 2 minus, and then don't forget these two because the stoichiometric power, the stoichiometric ratio for Ag plus is 2, so each raised to it must be square here or to the power of 2 here. Next, we have barium fluoride. The chemical formula is BaF2. Solid is in equilibrium with Ba2 plus and also 2F minus. You have to balance this, right? And then the Ksp expression will be concentration of Ba2 plus times concentration of F minus to the power of 2, right? Next, we have copper 2 sulfide. The chemical formula is CuS solid. It's in equilibrium with Cu2 plus aqueous and S2 minus aqueous. So the Ksp value, Ksp expression equal to concentration of copper 2 plus times concentration of S2 minus. Simple. Next, we have iron 3 hydroxide. So the chemical formula will be FeOH3 solid is in equilibrium with its ion, which is Fe3 plus ions and also 3OH minus ions, right? Balance. And then the Ksp expression will be concentration of Fe3 plus times the concentration of OH minus Q, or to the power of 3, right? Refer to its stoichiometric ratio. And then we have barium phosphate. Barium phosphate, the chemical formula is Ba3PO42. Is in equilibrium with its ion. Its ion is Ba2 plus, PO4 3 minus, and then you need to balance. Ba we have 3, and then PO4 we have 2. So next, it's time for writing the Ksp expression. So Ksp equal to the concentration of its ion. The ions will be Ba2 plus. So please use this modulus bracket first, and then times 3. Right? This is the ion. The ion is Ba2 plus. So concentration of Ba2 plus to the power of 3 because the stoichiometric ratio is 3, and then times the concentration of another ion, which is PO4 3 minus. This is another ion, the anion, okay, time to the power of 2 because the stoichiometric ratio is 2, right? Got it? And then we have tin 2 sulfide. S solid is in equilibrium with strontium 2 plus aqueous and also S2 minus aqueous. Therefore, Ksp equal to concentration of Sn2 plus, this is the ion, times the concentration of S2 minus ions. Next, using Ksp to compare solubilities. The higher the Ksp value, the higher the solubility of the salt. For example, we have magnesium carbonate. The Ksp value is 3.5 exponent negative 8. Meanwhile, another salt we have PbSO4. Ksp value is 1.6 exponent negative 8. So we have the same exponent. And then look at the values. Which salt do you think is more soluble? Yes, it is magnesium carbonate. Why? Because the KSP value of magnesium carbonate is higher compared to the KSP value for platinum sulfate. Therefore, it is more soluble. But bear in mind, you must compare KSP of compounds whose formula have the same total number of ions. Right? Here we have 1 ion, 2 ions. So, the total number of ions for magnesium carbonate is 2. The same here, we have 2. So it is valid when you compare the salt we have the same total number of ions, right? Let's say if you compare with barium fluoride, it's not valid because barium fluoride have 3 ions, total number of ions. So when comparing the KSP value, please make sure you are comparing with the same number with salt with the same number of total ions, right? So that's all for this video. Thank you for watching. Bye.